All right, well, we're recording this. Paul, you look like you're in outer space. That's pretty cool. I guess I should play with that. That way you guys can't see like my dirty laundry in the background or, you know, whatever. Paul, I can't hear you. Anyway, let's see here. Okay, so there's some of you guys here. Let's see. I'm gonna try, okay. I'm gonna try this here. I'm now sharing my screen here. Let's see if I can, it's a little choppy. I was hoping that I could open up Connect and I could like draw directly on some of these things. I'm not sure if it's going to let me do that though. Yeah, it's not going to let me do that. Okay, so what I was thinking about for today is we could do, I would work through a lot of the practice problems on forces on gates, because this is like something that kind of bothers a lot of my students. If anybody has a question about something they want to work on, we can certainly do that too. But I just kind of thought like, well, let's you know, let's do this because this is a common problem that people have. Where's Zoom? Let's share a whiteboard. And so where I'm going to get these problems from is I'm going to go and I'm going to get them from if you go to Connect, I created like a practice set for gates basically. Okay, can you guys see my whiteboard? I'm hopeful that you can.
Yeah, we can see it.
Okay, good. Okay, so what I'm going to do is on my other screen, which you guys can't see, but I'm going to pull up, I think I called it practice 5. And so hydrostatic forces on walls. And so I'm just going to kind of walk through this. A lot of my students really dislike hydrostatic forces. And so there are no questions. I created this in part for this purpose. Let me edit it. That way I can actually look at the questions. Okay. Here we go. These are my favorite ones. So I'm looking at problem in that hydrostatic things. I don't know what number it is, but it's called L-shaped hinged gate. It's problem 3.078. So 3.078. Okay, and I'm gonna go ahead and write down the given, the given and all that other stuff. So if you don't have that open, that's okay. And again, like I said, you know, whatever works for you guys. If this is not what you want to do at this time, somebody has something specific, then go for it. I love L-shaped gates. Actually, you know what? Let's not do this one. There's another L-shaped gate that we'll do an easier L-shaped gate first. Okay, so we'll do 3.076E. I don't know why it's got it 76E. Okay, and yeah, but most of my students hate these problems. I actually loved these problems when I took this class, but I think that's because I'm a weirdo. I had a lot more problem with momentum equation, but a lot of my students don't like these. Okay, so I'm going to start with this this one because I really like this one. And so basically what happens is, or I love L-shaped gates. I asked one on a test one time and it completely confused my class. And so I guess the nice thing about having this as an additional time on top of the regular time is that, you know, I can work some, you know, unusual things. What's up, Reggie? So yeah, so we got like a little hinge off the angle here. Oh, by the way, if somebody asks something in chat, could you guys either let me know or answer it? You know, if somebody says, well, what problem is he working or whatever, because, you know, I can't see chat right now. Okay, and so there's a weight right out here. I like these also because, you know, they kind of get at a lot of different concepts. Okay, and this right here is 15 feet. Okay, so let's see here. The flow of water from reservoir is controlled by a 2.5 foot wide. So this whole thing is, I'm just gonna say it's 2.5 feet wide. L-shaped gate hinged at point A. So this is point A right here. If it is desired that the gate opens and the water height is 12 feet, determine the mass of the required weight W. Okay, so hopefully it should be obvious, or maybe not obvious, but you know, obviously if I'd done a better picture. Okay, but if we, you know, as the water rises, two things happen. One thing that happens is, so we've got a pressure prism on this side of this gate like this. Okay. Okay, and as the water rises, two things happen to kind of like the resultant force that comes off of that pressure. So one thing that happens to it is obviously, well, maybe not obviously, but you know, the deeper the water, the greater the force. Okay, so that's important. The other thing that happens is as the water gets deeper, the location of the force kind of rises. Okay, the location of the resultant force rises. So these two things are going to have an effect on when it opens. Both of those are encouraging this thing. Well, I guess the greater force is causing it to open, although actually the force rising is actually causing a decrease in the moment around point A. So ultimately what we're looking for here is just to kind of like map out what it is that we're going to be doing here, is that the ultimate goal is we want a moment equation. And we're going to sum the moments around point A, and they're going to be equal to 0. And there's basically, oh wait, so this is given, okay, and required is we want to know the mass of the weight at A equal, or the mass of the weight W equals what? I don't know why they asked for mass, they could just ask for weight, but whatever. Okay, so what we want is basically, this is kind of where we're heading, is the sum of the moments around A equals 0. Because at that moment, any more water in this thing will open, okay? Or at least any more weight and it won't open. But you know, we want to get right at that point where this thing's going to tip open. So if we do that, okay, if I draw a little free body diagram here, okay, I'm going to do it around the point at A. So A has two forces, A in the X, A in the Y. We're not really going to have to worry about those because we are going to, I like Z, but whatever, it doesn't matter. We're not going to have to worry about those because, sorry, I'm doing this small because I don't have a lot of whiteboard space here. Hopefully you can still see it. Let me actually see this full screen so I can actually see what you guys are looking at. Come on, can you go big? There you go. Okay, it should be visible. Okay, so then we've got a weight going down right here. Okay, we got a force of weight right here, and we've got a force of due to the water. So we'll call that force due to the pressure right there. Okay, and so ultimately, you know, oh, and there's a stop right here, right? There's a force due to the stop, but right at the moment when this thing is about to open, that force due to the stop is no longer an issue. Like it just kind of goes away. So because you know it gets less and less and less, and then all of a sudden, you know, it's the water has removed the pressure on that stop, and it's gone. So that stop is this little black box right down here. Okay, so so in other words, and the nice thing about this is that the you know, there's a moment arm right here for this force of pressure, and there's a moment arm right here for this weight. Okay, so this equation is going to look like F of P times its moment arm, which I don't really have a name for it. I don't know what we want to call that. Let's just call that Y, I guess. Okay, and that's causing this thing to rotate, looks like counterclockwise, so we'll call that positive, minus the weight times its moment arm, which we happen to know from the diagram is 8 feet. So I can just go ahead and put 8 feet there if I wanted to. Okay, equals 0. And so you can see from that, we already know the weight. So all we need to know is we need to know both of these things. Okay, and these things are not necessarily easy. And so, you know, but they can be solved. Okay, so let's get into that and let's kind of start walking through that. So the first thing that I always like to do is I always like to, here's the solution, is I always like to think in terms of the shape. And what I mean by the shape is I mean, you know, if I'm swimming right here, Okay, so this is my eyeball. Maybe I have two eyeballs and a nose and, you know, some hair or whatever. Anyway, and I'm swimming over here. What do I see? Okay, because that's what the water is, that's what the water is pushing against. Okay, and in this case, it looks like I've got a 2.5-foot wide rectangle that is 12 feet deep. So my shape looks like this. Okay, so 2.5 feet wide, 12 feet deep. Okay, so once we do that, once we know what our shape is, there's some things that we can do that are going to make this maybe not easy necessarily, but a lot easier. And so there's 4 things that I like to identify for every shape. And the first one is the Y of the centroid, the H of the centroid. These two are very related. On this problem, they're the same. The I of the shape, okay, or you know, I've taught from 2 textbooks. I can't remember what this is. This is, I think in the current one, it's IXX. It could be different things. And then the area, okay? And once you have all of these things, and if you do them correctly, then solving for these other things become a lot easier. So YC, okay? So this is the depth to the centroid of this shape. So we look up on so there'll be a shape chart somewhere. It's in your textbook, and if you want to, you can just type into Google, centroid of, centroid of common shapes or whatever. And for rectangle, it's nice and easy because it's right in the center. Obviously, before we leave today, I'd like to work, something that's a circle or triangle or something where it's not so simple. But it's right there in the center of that shape. Okay. And so YC, we need to remember, and this is kind of the key, is that YC is measured. So this is from surface of the water to the centroid along the gate. Okay, so in other words, let's see if I can do this in green. It's going to go from right here down to the centroid. Okay, and I've kind of defined it on here. Here's my, it's halfway down, so that's 6 feet down. That's the same 6 feet over here. So the Y sub C is 6 feet. Okay. Now the H sub C is, in this case, it's the same, but it has a slightly different definition. Okay, it's from the surface of water to the centroid vertically. Okay, so in this case, they're exactly the same thing because the face is vertical. Face is not always vertical, but it just is in this case. So, so like if I were to draw that, well, it's the exact same drawing, right? So this is along the vertical direction. Okay, and again, it's the same 6 feet. Okay, so this is just gets to be 6. Okay. All right, the moment of inertia, this thing is, if you look up again in that shape chart, okay, it's 1/12. This is for a rectangle, base times height cubed. Okay, so it's going to be 1/12. The base in this case is right here. Okay, 2.5 feet. Okay, and the height is 12 feet. Okay, and I'll need a calculator for that. I can't do that in my head. 2.5 times 12. Oh no, cubed. Thank you very much. Equals, and we'll divide that by 12. Okay, so we get 360. So 360, and that's feet to the 4th. Okay, and then the area is going to be base times height because it's a rectangle. So 2.5 times 12 is what, 30, I believe? 30 feet squared. Okay, we'll go ahead and confirm that. Okay, so now that we've got these numbers, and please interrupt me, by the way, if some of these numbers if you don't know where they came from. We'll work some where HC and YC are different, et cetera, et cetera, et cetera. So what we're going to do now is there's basically 2 things we need to do, and these become plug and chug if you can identify those things. Okay, so the first thing is FP. Okay, so that's the force due to pressure. And that equals gamma HCA. Okay, in some of my old work, you might see this as gamma H bar A. That's exactly the same thing. It's just that I was using a different textbook when I did that. Okay, I actually prefer the bar, but I try to remember to use the C because this is the way your textbook does it. So the force of pressure. So, and the reason this works right here is what we're doing is we're basically taking this average height right here. So if we look at this right here, gamma HC, that is the pressure at the centroid. And basically I'm saying if I take the pressure at the centroid, then basically the pressure at the centroid is essentially the average pressure. So I'm taking the average pressure and I'm multiplying it by the whole area. So that's giving me the force. Okay, so that's why this works. Okay, so I'm not worried about the low pressures, I'm not worried about high pressures. Let's just find the average pressure. Okay, so anyway, so what this comes out to is if, like at this point, it's plug and chug, right? I've already got all of my stuff right here, all the stuff that's going to go into here. So gamma, this is water. So we have to say to ourselves, okay, are we in the metric or the SI system? Well, we've got feet, so it's going to be 62.4 pounds per cubic foot. Okay, HC is right here, 6 feet. And the area we've already calculated is 30 square feet. Okay. And, on a test, basically, by the way, so you'll know, like all I do for these is I'll go like, well, this one's at 1 point, this one's 1 point, and this one's 1 point. Okay. I'm looking to see that you're putting these things in the right spot. I mean, you know what they are. Okay. It makes grading really difficult because I have too many things to check for, but it's okay. Well, I got to get better at that because then I would be faster with it. But anyway, so if we multiply that, that's 11,232, 11,232. We check our units, pounds per cubic feet is being multiplied by feet and feet squared. So we get pounds. Okay. Okay. So the other thing that we need is we need YCP. So basically this is taking into account the fact that the force is not acting at the centroid, it's acting below the centroid, okay? And the way I like to think about that is, if I were to put my finger on this side, and I could put it in all kinds of different places, okay, if I put it right at the centroid, okay, which is where the average pressure is occurring, which might be about right here, okay, that might be the average pressure. If I put it here, you can see that this thing is gonna wanna spin this way around my hand, okay? It doesn't balance, okay? The net force is actually a little bit below that. Okay, and in this case, this is actually the easiest case. If you have a rectangle and the water surface is on the rectangle, it's actually going to be 2/3 the way down this. Okay, I know this already. So this is 12 feet. This is going to end up being 8 feet for YCP. But we'll go ahead and prove that right now. I hesitate to tell you guys that because then some people try to just use it as a rule of thumb, and they don't use it at the wrong time, or they confuse the centroid, which is halfway down in a rectangle, to where the YCP is, and it's only that's only where it acts in certain cases. So just be careful with that. So what we'll do is we'll do YP, okay, and then YC, and we'll say, well, how much further down is it? Okay, plus I bar or ice, I forget what this is, how this is annotated in your book, over YCA, okay? And so again, once you've done this box, this is just a plug and chug. Okay, so YCP. Now the YC, remember, is halfway down, so it's 6 feet. And then how much further down are we going to go? Well, we're going to add 360 feet to the fourth. And YC is 6 feet. And area is 30 square feet. Okay, now notice the feet cubed on the bottom, feet to the fourth on the top. So we're going to end up with feet. So YCP equals 360 divided by, looks like 180, so that's going to be 2. So we're going to get 8 feet. Okay. All right. So now, of course, I've scribbled all over the initial drawing. I wish I had more colors. We're going to try to use red here. So this thing is happening. This thing is existing, or whatever. So here's blue. So this thing is 8 feet down. 8 feet down. Okay, and we know how strong it is. It's this number right here, 11.2 kips. Okay, and what we want to do now is we want to say, well, okay, because we're now going to look into this moment equation in the upper right. Okay, So we need to know is we don't need to know 8 feet. 8 feet isn't good enough. We need to know, because we're summing our moments around A. And this, of course, is the trickiest part about these, or something that a lot of people miss on these things. It depends on where the hinge is, right? If the hinge were at the bottom, then in this case, we would want, well, this is 12 feet. This is 8 feet. So we would want 4 feet as our moment arm. But in this case, the hinge is on the top. So we've got 8 feet here. And let me do some red here so we can see. We've got 8 feet right here. But then I need to know how much further up is this. All right, and that comes from this 12 feet and this 15 feet. So this is another 3 feet. So my moment arm in this case is 11 feet. Okay. So, I mean, it's just kind of this last little step that a lot of my students overlook. So, stop, take a second, think about what the YCP is, and then, try to figure out how to solve that. Okay. So what we do now is we go into FP, and FP would be what, 11,232 pounds. And then this moment arm is going to be 11 feet. Okay, minus the weight, which I guess in this case, we're actually solving for mass. So I'll do M and then the G, which is 32.2 feet per second squared. And then we've got that 8 feet equals 0. So we can solve that, right? It's not really important what the answer is. I should note that just in case you're uncomfortable with this, what units are we going to get on that? Does anybody want to just tell me? Because it's going to make me a lot happier if you know this answer.
Slugs.
Slugs, yes, very good. I love it, right? Slugs are the worst. And they make my students so uncomfortable. And I totally understand that, especially because most people can't picture a slug. But just remember the slug is really big. So like a slug on Earth weighs 32.2 pounds. So, it's easy, like when I'm like, oh, what is a kilogram? And I'm like, oh, a kilogram is something that weighs like 2 pounds. And so I imagine I still remember in like high school physics, somebody saying like a dictionary. And so I always remember a dictionary is about a kilogram, and that's like pretty straightforward. Slug, I mean, anyway, so I'm getting 179.63, 179.63 slugs. It's also annoying because, like pounds has a nice symbol. This doesn't have one. So this is like, if we go to 3 significant figures, 180 slugs. Okay. Any questions? Okay. Then before I erase everything, I'm going to go find the next problem that we can work. Oh no, it's frozen on me. Don't do that.
In our book, the IXX has like a comma C. Does that matter?
No,
also, or it's just the same thing?
It's the same. Okay, this other L-shaped one is basically the same problem. Yeah, I can't ever remember how they format these things. So, okay, so yeah, good question. Any others? What I like about these two is I can almost leave this whole thing as is, since they almost always ask the same questions. Okay, so let's do this one. This one's pretty weird. Okay, so 3.073. It's a triangular gate. I like triangular gates. And I should mention that the things that I can vary when I give this to you. So this one right here is pretty straightforward. It is a rectangular gate. It's vertical. It has no gap between it and the surface of the water. This is a very straightforward one. And you'll see like the things that I can vary. Let's see if I can do them, kind of just scribble them real quick. So one thing I can do is I can put the gate on an angle. The angle could be this way or that way. I could change the shape from rectangular to circular to triangular. I can move it away from the surface of the water, which adds a tiny bit of difficulty. What else can I do? I could also curl it, curve the shape so that it's like this, which has yet to show up on a test, but every single semester I roll dice to see whether or not it's going to show up. And so it's got like a 1 in 6 chance of showing up. And so it just hasn't happened yet. Could happen to you guys. So just, be aware. Don't think you don't need to learn it. Just, it does make for a harder problem though. Okay, so I'm going to clear these drawings. I'm going to try to work through all the things that I can vary. Okay, so here, this is 3.073, 3.073. Okay, this is a triangular gate. Okay, and this one looks like, oh, this one doesn't have a hinge, which is fine. Okay, so looks like this. This one also, this sort of problem, oh, okay, well, that's not what I wanted to do. Okay, this sort of problem also throws people for a loop sometimes. I'm gonna draw it a little bit big. I guess it's nice to have a big drawing since that's what we're working with here. Okay, and there's a gate, right? You know, there's some sort of gate right here. The book kind of draws it in green. Okay, and then it kind of shows you kind of like, what does this thing look like if I'm swimming underwater? And the gate looks like this. It's what do they call this? An isosceles triangle. I used to teach 6th grade math, so I should know these like terms that don't really matter. At least I don't think they matter all that much. Okay, so then this distance right here is what they call D. This angle is beta. And then the distance down here to the bottom of this thing. And you know, one of the most annoying things about all of this is that we have to deal with a lot of geometry on these and a lot of trig. Okay, so the density of, it says take the density of water to be 1,000, which is what I always tell you to do. Or actually, I've never really specifically said anything. The density of water usually is actually taken to be 999. However, I think it's easier to just remember 1,000. So let's just go with that. So this distance D right here is 0.38 meters. Okay, so this is what's given. And for this particular problem, they want to know, okay. So they want to know F of P equals what? And they want to know what they call the line of action. Okay, so they're basically looking for YCP, I think. That's what I would be asking for if I asked you for the line of action. This is why we always ask for the moment, because it proves that you know where the YCP is. Okay, because sometimes you can just solve for the YCP and it doesn't mean you know what the YCP is. Okay, so anyway, so so let's go ahead and let's go ahead and get started. We don't need to do a moment thing here, so we're going to do the shape. Okay, and again, if you're in the water, you've got, you know, a set of eyeballs and you've got a nose and you're smiling because this is like super duper fun and you're not having to do math problems. And this shape looks like it's a triangle. Okay, and it's 0.7 on one side and 0.7 meters on the other side. Okay, and this one's actually kind of nice because it tells us all of that stuff. Okay, so now we need, and I think I'm going to change the order here. The last time I just kind of did it on the fly. We're going to do YC, HC, and then we'll do area because area is relatively easy. And then we'll do the moment of inertia next. So it's IXX comma C in your text, is that right?
Yeah, it's got a comma C.
Yeah, okay. All right, so with YC and HC, you kind of just do whichever one of these is easier for you first, and then you solve the other one. So we need to identify where, oh, by the way, thank you, sorry. I get so in my own brain, I almost get a little rude. Anyway, so we would need at this point to know, well, okay, where is Y sub C, where's H sub C? Okay, so they're different, okay? And in the last one, they were the same because it was vertical, but the H sub C is measured from here downwards, so that's H sub C. Maybe I should use colors for that. So H sub C is measured this way, and Y sub C is measured this way. But they're both going to stop at the same point, and we need to figure out what that is. So we go find our shape thing, and I just type in moment of inertia shapes, and usually, if you go to the, unfortunately, I'm not using Google, so I get kind of crummy results. But usually you can click on this pretty quickly, and for a, or you can just find it in your textbook. I should have that out right now, actually. Where is it? Here we go. List of moments of inertias for different shapes. Okay. Okay. Well, anyway, I know this one already, so I don't need to look it up. But hopefully you guys will look it up. You should have it in front of you so it makes sense to you. So whichever one you're using on an exam, you need to get used to using. Okay, you need to make sure that it works. Okay, so it's a third of the way up from this bottom edge. Okay, and so it's 0.7 over 3 from the bottom edge. Okay, so it's basically 1/3 of the height. Now it's important that you identify which side it's coming from, right? Now in this case, the centroid makes sense that it should be down towards the lower half because there's more area down here. So basically you're kind of looking for the spot where you've got half the area beneath it and half above it. I mean, not exactly, but more or less, okay? Or, hand wavy definition. That's not exactly correct. Okay, now notice that this though is on a diagonal, right? So it's helping me figure out the y. Okay, so the YC. So I know this is 1/3 of that distance. So basically this distance from here to there is 0.38 meters plus 0.7 meters. That's all this, 0.7 meters. And then I could come back that third. Okay, so, or I could just multiply that. Instead of going that full 0.7, let's just go 2/3 of that 0.7 plus 2/3 of that 0.7. Okay. Oh, good. That's not my dog working. Okay, so my YC becomes, how annoying that they give us a problem where they know that we're gonna have to divide by 3 and they give us 0.7. They could have given us 0.6. Okay, times 2 divided by 3 plus 0.38. I mean, even 0.38 is annoying. So right off the bat, we're already in, significant digits land. 8, 4, 6, 6, 7. Okay. Meters. Okay, I'm going to keep that in my calculator. All right, so now HC. So if I kind of draw this over here, so this is where this thing is happening, right? So both of these are going to the exact same point. Just one of them is going on an angle, the one we just solved for, and one of them is going straight down. Okay, so actually I'm going to draw this one right here. So now we have a nice rectangle. I mean a nice triangle. So we could do some trig on that. Okay, so here's my angle. It's the same angle as there, beta. We need to figure out what beta is. Okay, so how do we get beta? Okay, before I can get H sub C. So beta, well, let's see here. Well, we know that this side of this triangle is 0.9. And then I know this side of this triangle is 0.38 plus 0.7. Okay, so this is going to be, okay, we've got yet another triangle right here, right? That is also beta. Okay, so I've got, let's see here, the opposite is 0.9 meters. The hypotenuse is 0.38 plus 0.7, so that's going to be 1.08 meters. Okay, and that's the sine of beta equals that stuff. Okay, so if I plug that into my calculator, beta comes out to, let's see here, inverse sine of 0.9 divided by 1.08 equals, oh, nope, clear that, equals 56.443, 56.443 degrees. Okay. All right, so once we have that, I want to get H sub C. Okay, so H sub C that's this blue line right here. Okay, and I know that we know that this is that number right there. Okay, so I'm basically going to do this exact same equation again. In fact, it's completely silly to actually calculate the angle here, but sine of beta, 56.443, which I already know what that is anyway. It's this right here, equals, in this case, I guess it means the opposite, H sub C, over the hypotenuse, which is 0.84667 meters. Okay, and rather than solve this, wait, is that right?
So we could just treat this as like similar triangles also?
Yes, that was what I was about to do. That's a much easier way to do this. Okay, and in fact, a lot of times in a lot of these problems, they tell you it's a 3, 4, 5 triangle, and almost all of my students will go calculate the area, but you can always do similar triangles instead. And the thing is, what a lot of people don't think about is the fact that all of trig is similar triangles. That's all it is. Unfortunately, we use these weird names like sine instead of just ratio of sides. So yeah, you can do similar triangles. In fact, that's about how I was going to solve this. So we can just say, well, I already know the sine of beta is this, 0.9 over 1.08 meters. Just cross multiply, okay? And that'll also give you a more exact answer, right? So anyway, so we'll take that number, pull it out of my calculator, okay, times 0.9 equals divided by 1.08, 0, so h sub c equals 0.70555. 70556 anyway. Okay, boom. Okay, 0.70556. What's good at this time, at this moment, is to look at this number, and make sure they make sense to you. Okay, which one should be longer? Well, the y sub c is always larger than the h sub c because the h sub c just goes straight down. The y sub c, if it goes straight down, is the same, but if it's on an angle, it's something totally different. Okay. So now, okay, area. Okay, it's a triangle, so it's 1/2 the base times the height. Okay, so that's 0.49 divided by 2, so that's 0.245 feet squared. Okay, and then the IXXC. Okay,
so meters squared, right?
Oh yeah, sorry, meters squared. Thank you. I would have probably caught that eventually. Meters squared. And then IXXC. For that one, we're just going to, so again, find a nice chart that you like. And in this case, it's 136 the base times the height cubed, if memory serves, and I think it does. So it's 136. The base is 0.7 meters. I never like it when they have the same numbers in these spots because it makes it like when I create problems, I always give you different numbers. I'll never give you 2 and 2 because, or 0.7 and 0.7, because then I can't tell if you're putting the right number in the right spot. Okay. So that equals, let's see here, 0.7 to the 4th divided by 36. So some really small number. The other thing I hate about moments of inertia is I have no idea if my numbers are realistic, right? Like this one looks ridiculous to me. Like I'm kind of like, that seems wrong. But, you know, I can't, you know, I have nothing to base that on. It's probably correct. You know, it's just like, you know, sometimes you just stare at it, you're like, well, I don't know. Okay, so now that we've got that, now we can do, I'm going to go ahead and erase all this trig here because I think you guys are probably good on that. I wish there were an easier erase mechanism on this. Okay, so now we're going to split this out. We're going to do our two things. Okay, so F of P equals gamma H of the centroid. So again, remember, this is the pressure at the centroid. So it's the average pressure multiplied times the area. Okay, so the FP equals the gamma. We have to stop and think, what system are we in? We're in the SI, so we use 9810. Or really, I guess this problem specifically asked us to use rho equals 1000. So I'll go ahead and use that. So gamma is rho 1000. Well, gamma, remember, is rho G. So 1000 kilograms per cubic meter, okay, times G, 9.81 meters per second squared. So that's where we get the 9810. Okay, and then HC, we're just going to start plugging in, 0.70556 meters times the area, which is 0.245 meters squared. Okay, so that's just a, you know, calculator away, 1000 times 9.81 times 0.70556 times 0.245. Okay, and we end up with 1695.8. Okay, and so we've got meters cubed right here, canceling with meters cubed, gone, gone, gone. Kilogram meters per second squared, so that's mass times acceleration, so that's a Newton. Beautiful. Okay, and yeah, we're matching the book, so that's good. Oh, I guess if we were, since we boxed it, it should be, we want 3 sig figs, so it'll be 1.70 kilonewtons, okay, or that, okay. All right, okay, so then we want to know where it happens. So we look for YCP, okay, and it's the same formula, YC plus IXX comma C over YC times the area. Okay, YCP, the Y is the centroid. I mean, at this point, we just plug in numbers, right? You probably don't even need me to talk you through this. I'll go ahead and do it just in case there's something weird, but I don't think so. 0.0066694. I'm not going to be able to squeeze the units in there, which is annoying. 0.84667 times the area, which was 0.245, 0.245. Okay, so if we plug all that in, 0.84667 plus 0.0066694 divided by 0.84667.245. C's equals 0.87888. Okay, and that's meters. Okay, if you look at this, we've got meters to the fourth on the top and meters to the third on the bottom. Okay, so now what's the line of action? Now, to me, if something asks for the line of action, it has to be relative to something. So, you know, this would be fine because this is YCP. This is the distance from the surface of the water. So 0.879 meters from the surface. Okay, and that's measured along the face. Okay, so that's measured right here. Okay, it's measured from the surface down to where the force is acting. Here's the force acting right here. Okay. Okay, and that's how we do it. Any questions? I hope, by the way, that this is demystifying this process for you guys a little bit. People tend to kind of like, you know, it's a lot to keep track of. And if you look at a lot of my keys, I always do this little shape box. And to me, it's like, let's just think about these things one at a time. And once you've got that boxed off, it's like, oh, well, now I just got to, you know, let's just breathe and just plug and chug. Okay. And it's just remembering the difference between the YC and the HC. Okay. So let's see. We are at 11:47, so we still have half an hour. Let's see what else we can do. Well, I'm going to work as many of these as I can today, and then, you know, we'll move on to another topic next time, probably. And if there's any there you're like, I really want to do this type, just, you know, let me know. Okay. Let's do, this is a curved submerged surface, but it's a fill in the blank. That's not very helpful. That's also a fill in the blank. Let's see. Triangular gate, hinged plate blocking channel. No, we just did that one, basically. So if you look at 3.074, it's like it's like they're all like that, okay? Let's see here. Let's do a semicircular water reservoir. Okay, these are a bit harder. So we'll do a semicircular one. Okay, and let's see, it's either this one or there were two of these that I gave you. Quarter circle dam. No, these are both the same. Okay, we'll do quarter circle dam. That's 3.071. Oh, any questions, by the way? I mean, I shouldn't even have to ask. You can always interrupt me. Okay, well, let's clear all drawings. Okay, so when something is given to you and it's a quarter circle dam, or it's just any kind of other shape, then things get a little bit different. Okay, so let's see. Okay, let's do this in black. Okay, 3.071. Okay, and they call this the quarter circle dam. Okay, the water side of the wall of a 65-meter long dam, so the length of the dam is 65 meters, is a quarter circle with a radius of 7. R equals 7 meters. Determine the hydrostatic force on the dam and its line of action when the dam is filled to the rim. So this is a given. Required, it says we want hydrostatic force, F sub P, and the line of action. Line of action is really annoying on these. when the dam is filled to the rim. Okay, so full. Take the density of water to be 1,000. Okay, I'm not going to write that down. Okay, density of water is 1,000. Although you should do that for my homework, but I think it's a little silly because we always do that. Okay, so what we've got here, okay, and this one's a little bit harder. Okay, and I'm going to draw the picture kind of down here. Is you've got a semicircular dam, so it's like this. Okay, and that's got a radius of, radius of 7 meters, and it's full of water. Okay, now I'm going to do my best to draw that as if it's okay, to kind of give you an idea what's going on here. This thing is full of water all the way back to here, right? This whole thing is full of water. Let's see, so we can kind of do that. I wish I could like do like a touch erase, but that's not really going to work. All right, so anyway, something like that. Okay, and this thing has a radius right here. This is all 7 meters. Okay, this 65 meters, that's in this direction. Okay, hopefully that's not a terrible picture, I guess. Maybe we could like dot that up. Yeah, it's not horrible. Anyway, that's the idea, right? And so going off this way, we've got, anyway, that's the idea. So we've got this shape right here, and it's an abnormal shape. So really the way to do this, if you were, wanted to get really mathy with this, and I recommend you guys, you could even give this a try, is you could actually draw the pressure prism, and it's always perpendicular, and it looks, something like that. And you could actually integrate that over this area. And it should be doable because you know the formula for this area. And so that makes this a possibility. However, most of you guys don't want to do that. Okay, and I don't really blame you because it's a certain amount of work, right? So the clever way that these people came up with, and I think as I said in the videos, like I remember just being really excited by this when I saw it, because I was like, well, that's really clever, is that what we're going to do is we're going to draw a different free body diagram. So we're going to do this. So I'm just going to draw a free body diagram of the water itself. Okay, so this is free body diagram of the water. Now I'm not going to try to go in 3D because I don't want to get this confused. Okay, and so we've got a force of, I'm going to call this the force of, do they call it a levee or a dam? Quarter circle dam. So I'm going to call this the force of the dam. Okay, and we've also got a force of the water on this wall. Okay, so there's a pressure prism on this wall. It looks like this. Okay, and that's got a resultant, which I'm going to draw right here. Okay, and in other problems, normally a lot of times so usually like books will call this FH for F horizontal, and there's an F vertical right here. Okay, now it just so happens in this case that this F vertical we're not going to worry about, but I'm going to show you how to solve for it anyway, just in case. So really this F vertical is the density of the fluid on the top times the depth in that fluid. Oh, come on, go back. Don't do that. We don't want you. Okay, times the depth of that top surface. Okay, so that's the pressure at the centroid on the top times the area. And so that's how you would solve for this. It just so happens that in this case, we're considering air to be, basically the atmospheric pressure is 0. So this average pressure term here is 0 because we're using gauge pressure. Okay, because this is the top of it is open to the atmosphere. If I gave you one where this was at the bottom of a giant lake, you just need to figure out what this depth is right here and apply that. Okay, so that's really what you would do here. Okay, so in this case, I haven't gotten all of my forces for doing free body diagrams. And just as a heads up for those of you who struggle with like how to do a free body diagram, we want to remember where we're cutting the world off from our system. Okay, and I'm going to do this in green. So right here, I cut the world off from my system. So I need to think about the forces acting right there because I'm replacing the world with forces. And the forces right there, well, that's this pressure prism. Okay, and then I have to look for shear forces. Are there any shears right here? And the answer for whether or not there's shears in a fluid is there are no shears because it's hydrostatic. hydrostatic fluid never has shear. Okay, shear is basically created and it's, by movement, hydrostatic fluid. Okay, so that's this side. Now we look at this top side. Okay, and that has a force on it that in this case ends up being 0. And now we have to look at this side. Okay, and that is this reaction force right here, FD. Okay, once you have, and again, like, are there any shears over here? There's no shears because there's no movement. Okay, this top surface could have actually a shear if it was windy, right? So if there were wind blowing over the top here, that would change things. But we're going to assume not, because among the other things, you guys don't know how to deal with that. So, and then the last thing is, so those are all of the surface forces, and then we need body forces. And the body forces, I tried to think what these could be, and really it could only be magnetism and gravity. There might be some others, like probably if you were working small enough scale in physics, you could do strong forces and things like that, but it's things that attract this thing from a distance. In this case, we just got the weight. Okay, so we need to apply that here. Okay, the weight. Okay, so now we need to resolve all of these forces. And ultimately what we're looking for is we're looking for this one right here, because we're looking for the force on the dam, and the force on the dam is the opposite of the force. You know what, I forget how I usually do these. I usually call this force dam on water. Okay, and what we're looking for really is force water on dam. Okay, and those are equal and opposite. So, which kind of makes it's a little silly to write it that way, but it just helps me to kind of remember what it is we're doing. Okay, so let's begin. So first easy thing, this one goes away. Don't forget it if I were to make it go underwater. If this dam were somehow underneath, if the dam went vertical here and we just wanted the force on this semicircular section of it. Okay, so just be aware of that possibility. Okay, so now we've got to think about this force, because that one's a hard one. We have to think about this weight. Let's start with the weight. Okay, weight in fluids is gamma times volume. Okay, it could be mass times gravity, but usually it's easier to go this way. Okay, because the gamma we know, right? We're in the metric system or the SI system, so this is 9810 is the gamma, newtons per meter cubed, and the volume of this irregular shape is just this area, or this area times its height, okay, or whatever you want to call this, lateral dimension. So the area of a semicircle is the area of a circle, pi r squared, okay, divided by 4, because it's only, not semicircle, but quarter circle, because it's only 1/4 of it. And then we're going to multiply that times this height, which is 65 meters. Okay, and the radius here was 7 meters. Okay, so the weight of this thing is just all of that. Okay, so let's see, 9810 times pi times 49 divided by 4 times 65. Okay, some really massive number. 2, 4, 5, 3. This pi is such an ugly thing. It just ruins everything. 3, 9, 1, 2, 3, 4, 5. That 9 actually becomes a 0. Okay, so this will be 40. And that's going to be kilonewtons. Okay, really massive number. And you should expect this to be a massive number. I mean, this is a 65 meter dam, and this is all the water behind it. Okay, so it should be a big number. So don't be too scared by that number. All right, so now we need the FH. And so for the FH, again, we're going to imagine you're swimming down here. Okay, here's your eyes. Here's another eye. Okay, what do you see? So now we're going to do the shape. Okay, and the shape is it's a rectangle. Okay, what do you see right here? This is the shape that we're thinking about right here. We see a shape. Okay, and it's 65 meters long here, and it's 7 meters tall. And as soon as you can get that, then you're like, oh, now I see why doing it this way is not all that terrible. Okay, because I'm not gonna blast through this, because the YC and the HC are the same thing. Okay, I'm just gonna do that once. That's gonna be halfway down, so that's 3.5 meters. Okay, the area, well, that's just 7 times 65. What's that, 420, 455? I think. I'll go ahead and check myself on a calculator here, because if this were a test, I wouldn't want to miss those points. 455. And then the IXXC, okay, is, by the way, that C just means that that's the moment of inertia about the centroid of the shape. Okay, so it's 1/12 base times height cubed. Okay, 1/12, the base, 65 meters, times the height, 7 meters cubed. Okay, and of course they give us a 7 so that nothing is pretty. Okay, times 65. I guess it's good practice because nothing in the real world is ever pretty. At least I assume. I don't like the real world. You know, they always say those who can do, those who can't teach. I don't know if that's true or not, but I certainly prefer teaching. Anyway, so now we've got this. We can split this out and we can get our forces, right? We can figure out where it acts and we can figure out what the force is. So let's see here. Oh, I did forget something up here, so we'll do that in a second. But so we'll go FP. I'm doing this quick, by the way. I'm assuming that this is the third time we've done this. So just plugging and chugging, HCA. And remember, this is the pressure of the centroid. Okay, so FP equals 9810 newtons per meter cubed. HC is 3.5. And the area is 455 square meters. So again, we're gonna have a really big number. Don't be scared, that's because this area is large. Okay, so 9810 times 3.5 times 455. Can't do that in my head. Oh, God. 155 or 15622. And we're going to convert to kilonewtons because I don't want to write the rest of those digits. Okay, so really big numbers. I'm assuming the final answer in forces is going to be in meganewtons. And then the YCP equals the Y bar, the YC, 3.5 meters, plus I bar, or IXXC, so 1857.9 meters to the fourth, divided by YCA, so 3.5 meters times the area, 455. Okay, so YCP equals, let's see, 1857.9 divided by 3.5 times 455, close parentheses, plus 3.5 equals, okay, 4666, a whole bunch of sixes, 4.6667, 4.6667. My guess is that if there wasn't any rounding in this, this would have come out to a nice pretty 4 2/3, but there is a rounding in there, so it actually did not come out perfect. All right, so I'm gonna go back and I'm gonna erase this original thing because I wanna start thinking about the line of action. I want to think about all of this business, okay, because this is annoying. The line of action is my least favorite thing. I never ask it. So here's my shape. Okay, and I've got FP right here of whatever that number is. I'm not going to write the number. And it's happening down here at 4.6667, 4.6667 meters. And then we've got a weight. I don't know, where's that weight happening? Okay, now that's a problem. That's the thing that we forgot to do. So this is the weight. And then last, I've got a force over here of, where's that force? Oh, that's what we're looking for. Force dam on water. Okay, so so this is a little bit annoying. We need to know where this weight acts. And I'm gonna have to look this one up because I don't know this, I don't remember this, but it acts at the centroid of this shape, of this quarter circle. Okay, so we need to know the centroid, and I'm just gonna actually type this in. I'm gonna type in exactly what I want into Google. Just type in centroid of quarter circle. And, you know, obviously we could solve for this if we wanted to, but that would be really annoying. Here we go. Quarter circle, 4r over 3 pi. Okay, and it's important to look at that and to realize that's from the flat side. So this right here is 4r over 3 pi. Okay, so if r is 7, I'm just going to go ahead and plug that into my calculator. 4 times 7 divided by 3 times pi. Where are you at, pi? I don't know where my pi is. There it is. Oh, we just had a pi day, didn't we? Okay, so this is going to be 2.9709. 2.9709. 2.9709 meters. Okay. All right, so for line of action, I hate doing the line of action, but basically it boils down to what you're going to do, and I haven't done a very good job of this. Okay. Well, let's get the magnitude, water on dam. So the way we get that is we sum forces in the x equals 0. And basically we get this force equals the x component of that force. So I get Fp minus F DOW in the x equals 0. And it's the F DOW in the x is going to equal Fp. Okay, so I'm not going to rewrite this number right here, but that's how you do that, right? And then you do the same in the y. Okay, now keeping in mind that there might be a force up here as well, just so happens and in this problem there is not. And so you do, oh wait, this was FH, sorry, FH, to keep it consistent, FH. Okay, oh, and I called it FP. That's my dog being a jerk, I apologize. And so we've got F DOW in the y or the z direction, y, minus the weight equals 0. So again, F DOW in the y direction equals the weight, okay, magnitude. Okay, so in other words, and this makes perfect sense if you think about it, right? What is this thing pushing against? Well, it's pushing against two things. It has to support this weight, okay, and it has to push back against this horizontal force. That's it, right? It's not really, I mean, it's complicated, but it's not, conceptually, at least that idea is simple. Now, obviously getting these numbers are a little bit more complicated, but conceptually that's all that's going on here, okay? And obviously if we want to solve the resultant here, you know, F DOW, we can do that real quick. Let's go ahead and do that. F DOW equals then FP squared plus weight squared. Okay, so I'm just going to go ahead and plug in the x component, which is FP, or FH. Sorry, I did H. Here we go. This thing, so it's 15,622 or 3, I can't tell, kilonewtons squared, plus the weight, 24,540 kilonewtons squared, right? So that would give me my FDOW equals. Okay. I don't think it's really important that we get this number, but it'll only take a second. I know some of you, like in your notes, you like to have a completed answer. I am not such a person. I don't care, but we will try to, you know, accommodate as many of you as we can. Okay. Okay, so that's kilonewtons. Okay, so that's the FDOW. So the F water on dam, which is what we would report, would be 29.1, I guess, meganewtons. Okay, so that's what we would, so that's the water on the dam. Okay, the line of action. I hate getting line of action. I'll never ask you to get the line of action. I know that that's not good enough, but well, I mean, easy. Well, okay. The way that they want you to do it, and we'll just go with their way, is basically to just get the angle. Okay, and then have the angle. Let's just go. Let's just do it the way they want to do it. Okay, there are other ways that are more complicated and more complete. We'll go with their way because it's totally fine. So to get the angle, then you just do theta equals the inverse tangent of, you know, the vertical component 24,540 over the horizontal component 15,622, like that. Kilonewtons cancels like that. Okay, so theta equals whatever that is. Looks like it's going to come to, I'm not going to plug it in the calculator. I'm going to get the answer out of the book. So that's pretty much how you do it. Okay. So, so this angle is 57.5. And it's going to pass right through the center of curvature here. Okay. So, yeah. Any questions on that one? Are y'all still there? I know I've been yapping for a while. Okay, I got one thumbs up.
No, you're good. I followed it the whole way.
Okay, good. And you know, max required. That's fine. I don't know if we have anybody else in here. Do we just have the four of you guys? Let's see, gallery. Yeah, that's it. Just the two of you guys. Four of you guys. Two of you being me. Okay, so let me get back to speaker view. Oh man, I hate Zoom. Okay, here we go. All right, so let's clear all. And I think we can find, let's find one more. There's one other issue that I put in this. I've never actually asked this on a test, but I think probably a good thing to be aware of, because this is like something a little bit different, is, okay, yeah, I like this one. Okay, so 3.067. This one won't take very long, but it has a different concept than what we've just done. Okay, this one's called the compressor on a cylindrical tank. And okay, so here we go. So here there's like okay, there's something like this. Okay, and it's got air in here. And there's like water. And they're saying the water level is like right there. Okay, and this is going into a larger tank. Like this. Okay, so we've got, I'm just going to write everything they have here. I'm not sure if we need all of this. D. So air is at what they call P0 or P naught, I guess. And it looks like there's a valve right here of some sort. They don't say a whole heck of a lot about it. Okay, cylindrical tank is fully filled with water. The diameter of the tank is 0.55 meters. I'm not sure why they give us A. If you give us diameter, we have A. But anyway, in order to increase the flow from the tank, an additional pressure is applied to the water surface by a compressor. Okay, so basically they're going to pressurize this air up here. Okay, so we've got three possibilities. P naught equals 0, P naught equals 5 bar, and P naught equals, looks like 10 bar. Calculate the hydrostatic force on the surface A exerted by water. Okay, so we want to know the pressure, the force on this thing right here. Okay, obviously that's going to be coming from the inside. Okay, take the density of the water to be 1,000 kilograms per cubic meter throughout. Okay, so I'm going to do this, and I'm going to do this two different ways. We're going to be quick because we only got another 4 minutes. So the first thing we want to do is, again, let's think about our shape. Okay, and we want to know about what's going on this thing right here. So it's a circle. Okay, the area of the circle, pi r squared. Okay, or pi, in this case, pi d squared over 4. Okay, so I'm just going to plug that in a calculator. You guys, you know, holler if you don't like it. You know, I'm not going to put in 0.55. Squared times pi equals divided by 4. Okay, 0.23758. 758. That's meters squared. Okay, let's see here. The HC equals the YC because this thing is vertical. Okay, so it's going to be half of that, so, or half of the distance down. So it's going to be 0.275 meters. Okay, and the IXXC, what is that for a circle? Moment of inertia circle. Come on, give it to me. List of second moments of areas. So for a circle, it's pi r to the 4th over 4, pi r to the 4th over 4. Okay, so again, I'm just going to plug in, that could also be done in diameter, but we'll do 0.55 divided by 2. 0.55 divided by 2, so that's my radius. Raised to the 4th power times pi divided by 4. Super small number. 0.0044918. Okay, 918. Okay, and because of that r to the 4th, this is meters to the 4th. Okay, so I guess none of this really matters because we really only want the force, so we don't really need this. Okay, but we could, obviously if we wanted to, it never hurts. So the force on that circular thing, force of pressure on that equals gamma h c times a. Okay, so the force of pressure equals the gamma, 9810 newtons per meter cubed. Okay, hc, that's the depth here. Okay, that's 0.275 meters. And then the area, this number right here, 0.23758 meters squared. Okay, notice the meters cubed are going to cancel, and we'll get some big number. Okay, so 0.23758 times 0.275 times 9810 equals 640.93. 640.93 newtons. Okay, obviously if we report that, we'll say FP equals 641 newtons. Okay. All right, so that's the straightforward way to do this. But the problem is, so that is when our pressure prism looks like this. Okay, so then becomes a problem. What happens when instead of the pressure at the surface right here being 0, it equals something else? Okay. And I'll tell you what. So first of all, I need to convert bar into pascals, newtons per meter squared, because I don't want to work with pascals. So let's see, 1 bar equals, it looks like what? Looks like it's 100,000 pascals. So this equals 500,000 pascals, and this equals 1 million pascals. Okay, if the internet is correct, which I think on this, we can probably trust it. All right, so now what happens is we get a new pressure prism, and I'm gonna draw this in green, and it looks like this. Basically, the pressure at the surface is now something, that is what, 500,000 or 1 million, depending on which one of these we're solving, and everything gets worse. Or not worse, but everything gets higher by whichever number we've got. So we're either 500,000 pascals higher or 1 million pascals higher. So what we're going to do here, and I really love this because it sounds really complicated, and it could be, but what we're going to do is I'm going to split this into 2 problems. One problem we've already solved, and that's this problem. Okay, I already know what this is. Okay, I solved for that right here, FP. Okay, what remains is, let me do this in blue, this is what remains. Okay, something that has a pressure that is equal through the whole thing. So the nice thing is, if I want to know what additional force that is, so let's say, so this is part A. If I want to know how much force I'm going to add to go from A to B, and then again to go from B to C, because I add the same amount of pascals to go, I add 500,000 pascals in both cases, is I just need to know how much additional force I need to add. So the additional force is just due to this blue business. And so that's just the pressure times the area, okay? So I guess I could say the change in force is going to equal how much did this pressure increase? So the change in pressure times that area. Please interrupt me if that doesn't make any sense. So the increased force is going to equal, in this case, 500,000 pascal, 500,000 newtons per meter squared, times that area, which I've already calculated, which is this number right here, 0.23758 meters squared. So we're going to get newtons here. So the change in force equals 500,123 times 0.23758 equals 118,790. 118,790 newtons. Okay. So in other words, my answer becomes, in the first case, it's 690 newtons or 641 newtons. In case B, it's now increased by this much because I added this much pressure. Okay, so if I add 116 to that, I mean 641 to that, which I can do, but it seems a little silly because it's like so small. I'm going to go up to 119, well, I'm just going to do 119 kilonewtons. Okay, so I just took this and added that to it. And then if I add this to it again to get up to my, my next level, okay, so I'm going to add 118,790. Okay, I get 238 kilonewtons. Okay, so what seemingly is a very difficult problem, if you think it through, or if you kind of just, I don't know, then it becomes a lot simpler. Okay, and so adding pressure to the top is not really that big a deal. Now, the last thing before we go is that if you had to do a problem where you're like, well, what if we had to find what if this was a hinge problem and there was a hinge right here? And I had to think about, how would I find out where the center of pressure is? Well, what you would do is you would have two forces. Let's suppose we're in this case right here. Then what would happen is we'd have this 641, and it would be using this pressure prism. We would use these numbers, and we would solve for YCP. Okay, and so that would be acting somewhere like right in here. And then for this other pressure prism, for this force, this force right here, okay, that's this pressure prism. And that one is acting directly at the centroid because it's evenly weighted everywhere. So it would just act right here. Okay, so basically you would have two forces. Okay, and in this case, this force is so much bigger that it would be the only one that really mattered. But you would basically take this force right here and that force, and you would add both of them. So this one would be whatever that radius is down, and this one would be acting YCP down. Okay, YCP calculated from these numbers. Okay. So anyway, that's all the time we have. Thanks for coming, guys. There's only two of you guys, but hopefully this was helpful.
Yeah, this was definitely helpful.
Okay. So, and did that make sense, this last problem? We didn't really have a lot of time.
Yep.
Okay. Well, then I'll be here again on Thursday, and we'll just pick another subject, or if y'all want to work more of these, we can do those too. So just let me know.
Sounds good.
Okay, cool. Good to see you, Paul. Good to see you, Max.
Oh, well, one thing I wanted to say, it's not as much related to this, but in your email, you'd said someone complained that they wanted different videos for theory and problem solving, right?
Somebody wanted my videos to be shorter.
So I help run a YouTube channel. So one thing I think would be helpful for these would be if you added chapters. Do you know what I mean? It's sometimes when you go on a YouTube channel, it's got chapters in the video.
I can add those in without redoing the video, is what you're saying.
Exactly, yeah. So if you go into the description and you type in the timestamp, then it'll automatically put those into the video, and that might be helpful for people.
Okay, well maybe later this week I'll get to work on that, because that's a good idea. Let me write that down. That is a good idea, because I mean ultimately I'd like to redo them, but if chapters can be I mean, when I thought about redoing them, I was like, students can just stop at a stopping point. It's not really critical, but it would be nice if they could do that. Yeah.
Yeah, and then if they I want to skip to the examples, they can just click the chapter.
It will also help for when you know that you're on example 2 and you come back later, but you're on a different computer, so it doesn't remember where you were. Yeah, it's kind of nice.
Yeah, exactly.
Good idea. I have seen those beneath the things. I just never thought about how to do it. So.
Yeah, I got you. Well, if you ever need any help with YouTube, just let me know. I've got.
What is your channel on about?
Oh well, I'm an editor for this guy, and then I also have one that's a clip channel for this guy who's a Twitch streamer. I help him. I edit his videos and stuff. But
okay, all right, cool.
Yeah, but if you ever need help with YouTube, just let me know.
All right, I appreciate that, Paul. Thank you.
Absolutely. Have a good one.
I mean, I have to accept I'm a bit of a boomer at this point.
Hey, that's okay. That's why you have students like us that can help you, right?
Exactly. I appreciate it. All
All
right.
right.
All right. See you guys.
Have a good one.
All right. You too. See you, Paul. See you, Max.